Okay, welcome back, ladies and gentlemen. Okay, so we continue our derivation of the closed loop transfer function. As you can see, each term is being multiplied by the denominator of the term on the right-hand side of the 1 plus, of the entire denominator of the closed loop transfer function. It's a bit iffy right now, so we'll just clean up these steps. You don't have to do this every single time. Once you just get the hang of it, you can just one by one, skip steps, get it all done, over and done with. So as you can see, each term is being multiplied by the denominator here, this one. Okay, so mathematically, you can start cancelling out terms. So I'm going to cancel out these terms. And you're going to see how this entire thing becomes much simpler to analyze. Okay, so moving on. Once the simplification has been done. Right, I'm just going to skip ahead quickly for you guys so it can just become more. So I'm going to skip all those redundant steps. And then we just complete our closed loop transfer function derivation once we have a clean numerator denominator transfer function. Okay, done. So this is the basic form of our closed loop transfer function, and that answers our initial part to part A. But we haven't actually completed part A yet because we actually have to find the characteristic equation of our closed loop transfer function. So we get back to the question. It's asking for the characteristic equation of the closed loop transfer function. The characteristic equation is a form of analyzing the closed loop transfer function via just isolating the denominator of this closed loop transfer function. The isolation of said transfer function can be done via the characteristic equation, and once you get the characteristic equation, you can then, as I said, analyze it via the root locus plots. That will be in my future tutorials, and I'll be discussing what they are and what the purpose is of plotting those diagrams. Okay, let's just move on. Alright, so the characteristic equation. So we go s plus 9 s squared. So like I said, guys, this is just the denominator of the closed loop transfer function. 30 plus 0.2 times 2 is actually 0.4. So, okay. Okay, done. That's part A finished, complete. And that will get you 1 out of 1 for this bit. Okay, done. Now, moving on to part B. Part B asks, we need to use Routh criterion to determine the values of k for which this closed loop system will be stable. What does that actually mean? What is Routh criterion and what is k? Why are we looking for k for stability? See this k right here? The reason why we did this entire derivation of the closed loop transfer function is in order to extract this characteristic equation in order to analyze and isolate this k value. But that's only the initial steps of analysis. As I said, you can start plotting the root locus diagrams and you can start doing some other further complex analysis methods and whatnot. So we isolate this k term and we want to find the range in which this k value would create system stability or system instability. Okay? So, what do we do? Okay, so moving on. We have to expand the characteristic equation of the factorized brackets that you can see here. So we need to expand it in order to actually easily analyze the characteristic equation. So s to the power of 4 plus 41s to the power of 3 plus 351 multiplied by s to the power of 2. Can you see what I'm trying to do here? You notice how I'm going from order of power of polynomial highest to lowest, from left to right? You'll see why I'm doing this now. So 657 s and then plus a constant. It appears that I'm trying to do something here, and that is we gather each and every term that is in front of the polynomial s, irregardless of the power. Every single term. So there's a 1 here, 41 here. Oops, sorry. There's a 1 here, 41 here, 351 here, 657 here, and 810 plus 0.4k here. That's the constant, and mind you, this is actually in s to the power of 0. It's s to the power of 1. Now, Routh criterion. I'm just going to ignore the iffy theory and whatnot about Routh criterion and how it's actually came up in the first place. But a guy named surname Routh, whatever, came up with this intelligent method of analyzing a characteristic equation and its stability via k value. So, you don't have to always have a k value. You can always just use Routh criterion on a raw characteristic equation without a k value. And the reason why is I'll show you now. So you gather each and every polynomial here. Gather each and every term in front of them. And then you look at the highest order polynomial, which is 4. 4 means we begin our table of Routh criterion. This is a table. Now you need to memorize this stuff. You create a simple, let's just call this a 2 by 2 table, but in this form. Neglect this bit. So we start off here as, my bad. This is a 2 by 2 table, and then according to the polynomial number, which is to the power of 4 for our case, is the amount of rows you're going to have. So in our case, we're going to have a couple of rows here. So about roughly 5 rows. The reason why I said 5 rows, don't forget there's a 0 here. So it's 1, 2, 3, 4, 5 polynomial terms. So we start off with s to the power of 4. Okay, so remember, s to the power of 4, s to the power of whatever polynomial order you have, you start off as the highest above the table, and then you begin to descend the order of polynomial as you go down. S to the power of 1, s to the power of 0. Okay, now, here's a tricky bit. To begin your actual terms within your rows, in front of each polynomial order, you have to gather each and every odd term for your highest order polynomial. Remember this, guys. For your highest order polynomial, you need to gather each and every odd term. So initially there's 1, 2, 3, 4, 5 terms. Am I correct? Of course, obviously. So we've got 1, 3, 5. 1, 3, 5. So what do we do with these terms? We just simply do this. 1, and you just skip a few lines if you like. 351. Skip a few lines if you like. 810 plus 0.4k. Okay, can you see what I'm trying to do here? And now to the power of 3, the descending polynomial order. Now we gather each and every even term. So we get 2, 4. Oh, what's happened here? There's no 6th term. So what do? That's a 0. So we go 41, 657, and 0. Now our table is, the introduction and creating the table that we can then begin analyzing is complete. To begin the analysis of Routh's criterion, you simply start off your initial term for your third row down to actually start off those values. Mind you, it's 3 values. It's going to be the same thing, 3, 3, 3. It's always going to be 3 irregardless. Just remember that, guys. That actually does depend on your order of polynomial. If you have it to the power of 6, s to the power of 6, then you can actually have 5 columns. Yeah, 1. So you're going to have 1 column, 2, 3, 4, 5 columns. And that's when it gets a bit tricky and you might have to use your graphics calculator. Alright, so moving on. What you would normally do is you would just say, alright, 41 times 351 subtracts 651 times 1 divided by 41. Let's just not do that quickly. For now, what you have to do is just put A1 to make your life easy. Moving to this bit, you then multiply this term by this term. This times this. That is because I've moved here. Now moving to this section here, you're actually extending the cross multiplication that occurs.